Hello class, and welcome to part 2 of this interesting material or methodology that we call Masonry. So where we left off, I'm not going to give you a recap in the slide, but we basically talked about what was Masonry. Basically it's small units which can be easily moved. We also talked about how it started off being made of stone, and we basically just used rubble, and then we realized actually we should start cutting these blocks into repeatable shapes, because we can actually build walls easier that way. And that's when we started using other materials too, like concrete or clay brick. We also talked a little bit about bonding. We talked about English bonds and Flemish bonds and those likes. And then we also talked a little bit about certain terms and vocabulary used with masonry. So we talked about frogs and bats, not the animals. Now, very quickly, I want to talk to you about cavity walls. A cavity wall is basically a wall that you can build where basically you build two masonry walls out of stone or brick or concrete blocks, and you leave a gap in between them. And this is basically filled with a material such as foam or sponge or a bat. And bat, B-A-T-T, not B-A-T, don't get confused. And this is basically a way that water can seep out of the wall. If one wall gets penetrated, it's going to fall out. And so it provides very good insulation. So it just like many of you might live in a house with double glazing on the windows, and the house stays cooler in the summer and warm in the winter. It's because of insulation. A cavity wall is one way of doing that. So a cavity wall basically is filled often with a synthetic material. So here I think it's being filled with polystyrene. And yeah, the main advantage is insulation. It's thermal insulation, but also sound insulation. But it also has another couple of benefits. It can actually provide fire resistance, because basically air cannot get into the house as well. Of course, if you leave a door open, that's not going to change that. And it can also provide strength, in that basically you're building two walls then instead of one, so effectively you're getting double the strength. But you could just build one wall twice the strength, twice the thickness though. So the main reason is insulation. Now, what sort of benefits can you get with cavity wall insulators? Well, it can often reduce heat loss from a property, or heat gain as the case may be in summer in Kurdistan, by up to 35%. That'll mean that your house, however, do you know when you wake up in the morning at the moment in the summer and the house is pretty cool and you don't need to turn the AC on right away, and then by midday the house has got hot and you've turned the AC on? Well, that gain in temperature in the house is reduced by 35%. That's what insulation does. Azl in Arabic. I'm not sure what the word is in Kurdish. So how would you go about building a cavity wall with masonry blocks? Well, basically you would build two walls right next to one another, and you would probably have little ties which are called wall ties, and they basically stop the walls from leaning into one another, and so you've got an even gap all the way through. Now, there's a few advantages I've already talked about, the main one being insulation. Sorry, I forgot to talk about insulation materials. Yeah, there's a couple of examples. They're basically foamy, woolly fabrics, and they make very good. They basically can absorb heat, and so the heat is not transferred. They are insulators rather than conductors. That's another insulation material, so that's a closed cell insulation material. That sort of material works quite well in housing compared with the other two pictures because it can't absorb water, which is a big problem. That's another closed cell one, which is good. So having said that, we'll go on to brick masonry, but one other thing, I do want to talk about a couple of disadvantages with cavity walls. The main one being is that if you're building a thicker wall or building two walls, it's going to add a lot of expense, isn't it? And the other big disadvantage is it's going to reduce the overall size of the rooms in the house if the walls are thicker, because they're making room for these cavities. So I have to say cavity walls are slowly dying out because of those two things, but you do see them from time to time in Kurdistan, so I thought I'd better mention that. I'm now going to talk about materials for making masonry blocks. Now we've already covered stone, and we talked about rubble masonry and ashlar masonry. I'm now going to talk about brick masonry. Now when I talk about bricks, I am not talking about concrete blocks. When I use the term brick, I mean oven clay. A clay that has been heated to a very hot temperature, and it forms this hard, strong material. And so it's usually this yellow or red in colour when clay has been heated. So you see oven clay bricks around Kurdistan a fair bit. All of the old bazaar and the new bazaar, the citadel, that's all in clay brick. Some houses in the wealthier parts of town often use oven clay bricks as well instead of concrete blocks. The reason they do that is because it's a much better material, because it's a very good insulator. So far, all we've considered so far is the shape of masonry blocks. So we've talked about the sizes, whether there's frogs or cavities in them, the dimensions, the nominal dimension, the coordinating dimension. But now we're actually going to look at the actual material of an oven baked brick. We're looking at the material of a material, kind of like Inception, isn't it? So we've already talked about stone, but we're going to cover briefly concrete blocks. But right now we're going to cover oven baked bricks. So with an oven baked brick, what is it? Well, it's basically clay, just mud that has been dried and heated, and basically when it's heated it forms brand new chemical bonds. And these bonds will basically form new molecules inside the clay which will be stronger. And there will be more of these bonds the higher the temperature that you heat the clay to. So at around 400 to 700 degrees Celsius, you have iron carbonate. That forms iron oxide, and carbon dioxide is blown off. And iron oxide is stronger than iron carbonate. Magnesium carbonate goes to magnesium oxide at around 400 to 650 degrees Celsius, and calcium carbonate goes to calcium oxide at around 700-800 degrees Celsius. Then that calcium oxide, at a really high temperature, that will react with sulfates in the air. That's found in the clay as well, and it forms calcium sulfites, and they are really strong, those bonds, and that happens at over 1000 degrees Celsius. Now this is not exhaustive of all of the chemical reactions that take place in masonry oven clay bricks. This is just a selection. I think there's probably hundreds of different reactions that take place, but I'm not going to test you on this. All you need to know is the hotter the oven, or kiln. Kiln is the word we use for this. Oven is something for cooking food. Kiln is for heating materials. The hotter the kiln, the stronger the brick, because you're getting more of these reactions taking place, and you're getting more of these chemical bonds forming. That's why we can take mud, which has very low strength, off the banks of a river, and then we can make it into a brick which might have 20, 30, 40 megapascals of compressive strength. How did we do that? Well, we basically put it under high temperatures. So oven clay bricks have been happening for a very long time. But it started off without ovens. It started off where these bricks, clay was basically just being heated in the sun. So I don't know if you're familiar with this city in that picture. This is Kurdistan. This is Shibam in Yemen. It's a pretty amazing city. You can see those buildings there. Some of them are about 14 stories high. They're very old. They're about 700 to 800 years old. So the Yemeni, they believe that they invented the skyscraper before Manhattan, before New York. They said we had the world's first downtown. And I think they're probably right. But incredibly, that you can see there that they don't really have a lot of stone in the vicinity. It's just sand and clay. How did they find a material to build their houses? Well, they basically heated the clay using the sun, and they were able to make bricks using the sun to heat the clay. And they're not particularly strong. I would say that they're about 5 megapascals in compressive strength. So the walls have to be very thick. And you can see the shape of those bricks too. They're actually fairly square in shape and quite shallow in depth. And that's basically so the sun's heat can penetrate them. But they were able to use these bricks to make massive high-rises. Now, later, people realized if we actually heat the bricks using oven, we can similar to ovens we would use for making dinner, we can actually increase the strength of the bricks. They began to notice the higher the temperature, the higher the strength of the brick. And they didn't understand all the chemical reactions taking place, but they recognized that it increased the strength. And equally, if you increased the pressure, it would also increase the strength, because basically increasing the pressure will basically increase the rate of reaction, similar to heat. So then around about 500 years ago, people started making these oven kilns for baking bricks. And so you can see there they've got a big oven, and on top of that they've actually got bricks which are being heated so that they become stronger. This is another one that's in India. A friend of mine took a photo of this, so you can see this is a clay brick factory. They're making bricks here, and you can see the kiln where they're making it. And then they started to realize, actually, if we start putting pressure, we can actually increase the temperature and also increase the rate of reaction and make the bricks even stronger. So here's another oven, and you can see that this one's actually got a roof, and it's got all of these poles, tree trunks leaning into it to try and increase the pressure so that the walls of the kiln don't fall out. And that way they can increase the pressure and improve the strength of the oven-baked bricks. And this one is actually one from Philadelphia. This one is about 200-300 years old. This is quite close to actually where my wife was born. My wife's American. She was born in Philadelphia. And this is an old kiln for making bricks. And this is very old. It's about 200-300 years old, but it's still operating, believe it or not. It's a very old business. You can see they're still bringing bricks out of that kiln. But basically they realized the higher the pressure, the stronger the brick we can make. And so you can see there that's actually a pressure vessel. That's why it's got a spherical dome on it. And you can see the small doorway at the front there. That's where they put the soft clay bricks in, and then after they've been heated they bring the hard, strong clay bricks out. But these days things are a little bit more advanced. Now we have far better kilns, and we can often bring brick firing kilns up to temperatures of 1800 degrees Celsius. Incredibly hot. The people of the Industrial Revolution would never have been able to achieve that, and they must they may also be pressurized containers to increase the rate of reaction. That means you don't need to heat the bricks for several days, only several hours. And you may notice here that these kilns, they themselves are made out of brick. Well, that's because it can't have it needs to be made out of a material that has a very high melting point, so it doesn't get destroyed. So actually, usually the kilns themselves are made out of bricks that these kilns themselves will be making. Now, it's very important that you do not exceed the melting point of the clay material, otherwise things like metals and things will start seeping out of the clay. But for the most part, that's going to be above 2000 degrees Celsius. So at around 1800 degrees Celsius, we're basically reaching 2000 degrees Celsius. You start to reach the melting point. Sorry, I said 200. So at about 1800 degrees Celsius, we've sort of reached the upper limit. That means we can't increase the temperature anymore and make our clay bricks even stronger. They'll start melting at that point. So basically the technology we're using for oven clay bricks, we're getting them about as strong as we possibly can. So how do we manufacture clay bricks? Well, there's a video that I'm posting online, and I recommend you watch it. It's going to be on Moodle, and you can watch a clay brick being made. It's very exciting. But basically, you've got a bit of a process. First off, you're gathering the raw material. So you can see there in the top left-hand corner, you can see they're actually collecting clay and probably a bit of shale there as well. And then they're storing it, and in that storage they're probably drying it out a little bit too, and then it's being crushed. That's so you don't actually get big rocks and pebbles inside the material, because that's going to affect the strength of the clay brick in the end. And then you send it to something called a pug mill. That's where you actually mix it with water. And so you turn it into a really thick mud, if you like. And then you screen it. You would, after crushing it, you would grind it. So you're making it into really small particles. And then you would screen it. That means you're getting out any of the big pebbles. And then with that very fine powder, you would then send that to a pug mill. Sorry, those arrows aren't really that correct. So you go from top left to top right, and then from top right to bottom left to bottom right. So here we've made it into this thick, gooey paste here at the pug mill. Now, after doing that we actually start shaping the clay into a brick. So it's not that clear there, but this thick, gooey mud, we're actually pushing it through an extrusion machine, and there we're actually making it into a nice long sausage, which is rectangular in its profile. So that's what's happening. It's beginning to look a little bit more like a brick now, isn't it? Now, another way you could do this is without extrusion. You could actually have mold boxes where basically, as it's coming through in the extrusion, these mold boxes will roll down and press the extrusion into individual brick shapes. And so you can see the bricks there, in their molds in the top center. And then you put it through a squeegee. Now, a squeegee is a bit of a funny word. I like that word, squeegee. But basically what you're doing there is you're basically compressing the clay so that if there's any air bubbles, it's being taken out, and so it's being squashed. The final thing is you stack all of the bricks so they come out, and here you can see people hand stacking them. And remember, these bricks are still very soft and muddy, but can you see how people are placing them? They're actually leaving big air gaps in between the bricks. That's because you need to heat them, and so the more surface area, the higher the temperature you're going to be able to heat the bricks. So this is the video. I don't know if this is going to show. If not, it probably won't. But try to watch this. I'll send this as a separate link too on Moodle if this is unclear.
Bricks are often made of shale, a lightweight rock that splits easily into thin layers. Quarry machines dig 40 centimeters down to expose the shale to the elements for 2 years. This weakens it, making it easier to process once it gets to the factory. A 4-foot-high stone wheel with a steel tire grinds the shale into powder. It grinds up 50 tons of shale per hour. A screen sifts out any pieces that need more grinding. The powder goes to the pug mill, which mixes it with water. This makes a thick paste that will next go through the extrusion machine. The extruder forces the paste through a rectangular opening to form one long continuous piece called a slug. At the same time, it shaves off the crustier top layer to expose what will become the face of the brick. If this gray shale mixture is fired as is, it'll naturally produce a red brick. To engineer a different color, they coat the slug in sand mixed with an oxide mineral such as zinc or iron. Next, they texture the surface with a textured roller. This is just one of many popular designs. Then, a large knife comes down like a guillotine and slices the slug into 5-foot lengths. You might be wondering where those 3 holes came from. Well, remember how the paste goes through the extruder to form the slug? Inside are 3 pins. They make 3 holes designed to decrease the brick's weight. Out of each 5-foot length, they cut 20 3-inch bricks. The ones on the ends are uneven, so they go back into the mix to make new slugs. Next comes the delicate job of stacking these newly minted bricks to be. A machine first separates them. Then, using inflating bags, it grasps them, raises them, then stacks them. Meanwhile, the water in the bricks is starting to evaporate. To hasten that process, the bricks go into a dryer for 2 days. The dryer gets its hot air from the heat generated by the kiln, where the bricks go next for firing. The kiln is really a giant oven. It bakes the bricks at 1,040 degrees Celsius. That's almost 2,000 degrees Fahrenheit. One and a half days later, the bricks are ready. The transfer machine takes them out of the kiln. But before they go to market, a technician does a quality check. He weighs and measures a sample to see if it meets the design specifications. Bricks are supposed to absorb some water, but not too much. Yet if they repel water completely, they'll also repel the wet mortar the masons use to stick the bricks together. So to test absorbency, the technician breaks a brick in half. He weighs it before and after soaking it in water for 24 hours. By comparing the weights, he can see how much water the brick has absorbed. Once the batch gets the okay, they stack the bricks into cubes of 500 to 600. Each brick weighs 5.5 pounds, so each cube weighs in at about 1/4 ton. Brick is one of the sturdiest building materials around. It doesn't rot, fade, warp, or dent the way some other materials can. Bricks are also energy efficient. They absorb heat to help cool your house in the summer and hold heat to help keep it warmer in the winter.
Yeah, I don't think that's going to be clear, so watch that video in a separate link on Moodle. So I have a question for you. Why can't we make big massive walls or slabs like we can out of concrete using clay oven bricks? Well, masonry blocks have advantages because they're easy, because people can move them, but sometimes we want to have big blocks like this because maybe we want to build things quickly or what have you. Why can't you use oven clay in the same way that you can use concrete, where you can make basically any shape you want? Why is it only really possible with masonry bricks? Well, it's because if you wanted to build a big slab like that out of oven clay, you would need to build a specialist kiln. It's going to be massive, and you're going to have to heat it to 1800 degrees Celsius. It's going to be far too expensive for a one-off slab. So it only really works if you're doing, financially and economically, if you're fire blasting and oven baking clay in a shape that is regular and repeated, and you can make thousands upon thousands of units, something like a masonry unit. The other issue is if you have very large shapes like that, it's very hard to heat the clay, because basically it's going to get heated on the surface, but in the middle it's still going to be cool, and so you're going to end up with parts of the clay which are going to be on the surface where it's going to be very hard and strong, but in the center it's still going to be soft and weak. So there's sort of a maximum size that you can use when doing fired clay. So let's talk about some properties of clay-fired bricks. The first one is compressive strength, and it's quite amazing that clay initially, when it's just mud, it has very little strength, maybe only half a megapascal maybe, but once you heat it up and you get all those chemical bonds and reactions happening, it's going to end up with a compressive strength of anywhere between maybe 5 to 20 MPa. That's pretty good. Just for comparison, the concrete blocks that you normally find in masonry here in Kurdistan, they have a compressive strength of anywhere between 10 to 15 megapascals. So clay-fired bricks, they can actually be strong enough for building any two-story house quite easily. There's no reason why a lot of the houses being built in Kurdistan that are being built currently out of concrete blocks couldn't be built out of clay bricks. Now, it's also got a very low modulus of elasticity. If you remember when we did modulus of elasticity with concrete and aggregate, the modulus of elasticity for clay-fired bricks is about 30 GPa. It's absolutely tiny. That means it can't be stretched or squeezed. It's a very stable shape, which makes it very good for building things. But this is one of the very good properties of clay-fired bricks, is that it's got brilliant thermal insulation. 0.3 to 0.8 watts per meter Kelvin. You're thinking, what on earth is a watt per meter Kelvin? Well, yeah, let me explain that. A watt is basically the amount of energy that is required to heat a room that has a wall of 1 meter thickness of the material, to raise the temperature by 1 degree Kelvin inside the room by applying heat and wattage on the outside. So if you were, let's say that you were living in your house and it had no doors or windows, you were just sort of trapped, if you like, and you were surrounded by a wall that was made out of clay-fired brick, and it was exactly 1 meter thick. I would need to fire 0.3 to 0.5 watts of power at the wall in order for the temperature inside to be raised by 1 degree Kelvin. So it's all a little bit confusing. It's a bit of an odd unit, but what you need to know is that basically the lower that number, the better the insulation. And so clay-fired bricks are very good insulators. That's quite a low number, 0.3 to 0.5. It's pretty low. And I'll have to say that I have been to a few of the houses that have been made out of clay-fired bricks, and they're a lot more comfortable than the houses that have been made out of concrete blocks. The reason for that is concrete blocks have very poor thermal insulation. It could be anywhere around 2 to 3 watts per meter Kelvin. And so houses, they have a tendency to get very hot in the summer and very cold in the winter. You know what I'm talking about, don't you? And so, clay-fired bricks have good thermal insulation. I was actually talking with a very old lady from Erbil. She was in her 70s. She actually lived in the Citadel many years ago. She lived there for the first 20 years of her life, she said. And now she lives in a house in Bakhtiari, and it's a modern house, but it's built from concrete blocks. And she said that her house in the Citadel, made out of clay oven blocks, clay-fired bricks, they never worried about having AC. because they didn't need it. The house was always cool in the summer and warm in the winter. But now, in her villa, they are always using the AC, and even then they're often uncomfortable. So, yeah, clay-fired bricks. I think that you should be using clay-fired bricks for a lot more of your buildings here in Kurdistan, personally, because of thermal insulation and a few other reasons. The downside, though, if there's a disadvantage, is they're a lot more expensive. I think for every concrete block you buy, it costs about 250 dinar. For every clay-fired brick you buy, it's much smaller, and it's about 1,000 or 900 dinar, I think. So effectively, you're going to be adding $10,000-$20,000 to the cost of a 2-bedroom house if you build out of clay-fired bricks, and that's why most people don't do it, even though it's a much better material. It's also fire resistant, so that's a really good thing, especially if you're building a residential house. A very good property to have. In New Zealand, most of our houses are built from wood, and it's pretty common to hear stories of people's houses burning down. I don't hear that happening too much here in Kurdistan, though, because you're using fire resistant materials mostly. It also has a water absorption, so this is basically porosity. This is the absorption capacity of 5%. So this means that if I weigh the clay-fired brick and it weighs, let's say, 100 grams, then I soak it in water for maybe 24 hours, and then I take it out of the water and I let the surface dry off it and I weigh it again. It might weigh 105 grams. It's increased in mass by 5%. And that's because of pores inside the clay-fired brick. So remember, clay normally has a very high porosity and absorption capacity of maybe 20-30%. After we fire it, it brings the water absorption down. And remember, porosity is a bad thing, because basically if it's high porosity, then the material will break down and it will degrade. There will be no durability with the material. However, for masonry blocks, you do need some porosity. You can't just use a material that has 0% porosity. Let's think of a material that has 0% porosity, something like glass, okay? Now, if I wanted to build a house out of masonry blocks and the blocks were made out of glass, be a bit strange, wouldn't it, to build a glass house made out of masonry blocks? The glass will not stick to the mortar, because the mortar needs to react, meaning that the water in the mortar needs to actually be absorbed into the block, into the masonry block, in order for it to stick the blocks together. If you have no porosity, then the masonry blocks will not stick together and you can just knock them over. There will be no strength. You need to have some porosity, and it needs to be about 5%, and clay-fired bricks deliver that. So remember the strength, it's about 20, it could be anywhere around sort of 5 to 20 megapascals. That's influenced by a few different things. It's influenced by the composition of the clay. So if the clay has a lot of ions inside it, it's going to be weaker than if it's a clay that has a lot of magnesium or calcium ions inside it. It's also influenced by the temperature. Remember what I said, the higher the temperature, the higher the strength. But also the method of manufacture. That can actually have a small influence on the strength. Basically, if you're heating it for long enough or not, and also if there's pressure in order to bring down the time required to heat it. that can influence the strength. Now, remember what I said, that it's a similar material to concrete in that it actually has pretty good compressive strength, but it's a lot weaker in shear and tensile strength. Now, what can you do to improve the shear and tensile strength of a masonry block? Well, one thing you can do is you can add fibers inside the brick. So you mix fibers inside the mud and then you heat it. So these fibers basically give it internal tensile reinforcement, if you like. And increasingly these fibers are being made from steel fibers or maybe even fiberglass fibers. But traditionally, this started happening over 1,000 years ago with sun-baked bricks. They were just using grass, they were just using straw. And if you go down to the old bazaar area, old Erbil, and you look closely at some of those buildings, you will notice that there's actually a lot of straw inside the bricks. This is actually a picture that I took here in Erbil. I don't know how old this house is. I believe it's probably around 200 years old, around the era of no, probably a bit younger than that. It might be 100 years old, let's say, because it wasn't on the citadel. It was down below in the bazaar, and yeah, it was. So it was probably during the Ottoman occupation, and yeah. Having this fiber, it increases the shear and tensile strength of the masonry block. Now, it increases the tensile and shear strength of the block itself. It may not necessarily increase the shear or tensile strength of the masonry block wall. Why not? Because it's probably going to break the wall if you strike it or you pull it apart in tensile forces along the mortar and not along the blocks. So I'll be talking about how you can improve the shear and tensile strength for masonry walls in a little bit. But yeah, the earliest place that we know that straw was used to actually create reinforcement for clay oven bricks, it actually goes back to around 6,000-7,000 years, and it has to do with the pyramids. So I don't know if any of you know your history, but the Egyptians, they built the pyramids using slaves. And one of the people groups that was enslaved by the Egyptians were the Jews, the Hebrews. And this is written about in the Bible, that the Jews were slaves in Egypt, and basically the Jews asked Pharaoh if they could have the day off to celebrate one of their religious festivals. And Pharaoh said no way, and because they had the audacity to ask him this, he actually made their work harder. He said that the same day Pharaoh commanded the taskmasters of the people and their foremen, "You shall no longer give the people straw to make bricks as in the past. Let them go and gather straw for themselves." So they were making clay bricks, and they were basically being given straw to mix in with the clay mixture, so it would have this tensile strength. But then from then on, they were told, now you need to go to the river and collect straw and cut it yourselves and then mix it. So their work got a lot harder. But anyway, this is all biblical history. But in terms of engineering, how is it that the pyramids have lasted so long? They're about 6,000-7,000 years old. Well, it's because of their high strength and high durability, and part of that is having very good tensile strength. and that's caused by having a straw inside the masonry blocks. So we've talked a little bit about thermal insulation, but I'm just going to talk about this again. Basically, the measure of thermal conductivity, this is basically about how easily heat transfers through a material and is transmitting. That is given the form lambda, but we measure it in watts per meter Kelvin. So remember, insulation is the opposite of conductivity. It's how well a material stops the conduction of heat. And so the smaller that number, watts per meter Kelvin, that's how much power needs to be applied in order to heat a temperature of one side of a wall by 1 degree Kelvin when the wall is 1 meter thick. The smaller that number, the better the thermal insulation, and clay bricks are considered good insulators. As I said, it's around 0.5 watts per meter Kelvin. It's very low. So let's just look at this for comparison. Air has quite a low insulation value, 0.023 watts per meter Kelvin. Many of you are thinking, well, why does it get so hot and cold so quickly outside? Well, that's because of diffusion. Basically, wind is constantly mixing the air, so you don't have any insulation outside. But if you actually have no movement and you have an air pocket, it has very good insulation. That's why things like cavity walls or double glazed windows where they have a layer of air, they are very good at insulating. Polystyrene foam is another thing which has very good insulation. Of course, glass is another one. But timber, it's pretty good. But the issue with timber, remember, this is a measure of watts per meter Kelvin, and timber is usually a very thin material. So what's going to be easier to have if you have a wall that is 10 centimeters thick, and you've got two walls that are both 10 centimeters thick, one is made from brick and one is made from timber. Sure, the timber one is going to have better insulation, but are you ever going to get a 10 centimeter thick wall with timber? No, you're not. With those other materials, air and polystyrene, water's got reasonably good insulation as well. They have no strength. So you can't build your house out of water. You can't build your house out of polystyrene foam or air. That's impossible. What about glass? Glass has strength, and boy, that has really good insulation, 0.035 to 0.06 watts per meter cubed. Well, that's fantastic, isn't it? Why don't we build houses out of glass? Sure, we could just paint the house, and the bits where we want windows we could just not paint. Well, that's because of expense. Glass is very expensive. If we were going to build walls out of glass that are going to be 10-15 centimeters thick, or whatever you need for the strength of the house, well, that's going to cost hundreds of thousands of dollars. It's just not doable. So we're left with materials, if we're building walls with any sort of structural analysis, something with basically some strength to it. Look at bricks compared with concrete blocks at the bottom. A concrete block is a very poor insulator, 2 to 3 watts per meter Kelvin. So basically, this is quite amazing. This is why Kurdish houses are so hot and uncomfortable in the summer and so cold and damp in the winter. It's because they are built from concrete blocks and they have very poor insulation, very poor. And that's why we use AC so much here. Right now I have the AC going on in my room basically for maybe 7-8 hours of the day. If the house was built out of clay oven brick, I probably would turn it on maybe for only a couple of hours a day. So that's a big downside with concrete blocks. Now, regular concrete has slightly better insulation. It's sort of 1.2 to 1.75 watts per meter cubed. Watts per meter Kelvin. So basically, it's not that great concrete, but that's normal concrete. Concrete blocks are made from very poor quality concrete. And so with concrete blocks, the sort of blocks you see lying around on the street or outside construction sites all the time in Kurdistan, they have even worse insulation, 2 to 3 watts per meter Kelvin. I actually think that this was a figure I got for concrete blocks in another country. I suspect it's actually worse in Kurdistan. I think your concrete blocks might have a thermal insulation of maybe 5 watts per meter Kelvin, but I haven't tested that. But anyway, if you look at that machine on the right, that's the machine for testing thermal insulation. It costs about $15,000. As of yet, UKH haven't approved the expenditure for the building materials lab for that. But basically, it's basically trying to work out how much power is needed to heat a material by 1 degree Kelvin, assuming that material is 1 meter thick. Now, one other thing. Why are concrete blocks built from low quality concrete? We'll talk about that later, but that's just a little tidbit to remember. Okay? Now, remember the absorption capacity. This is basically a measure of porosity. We did this with aggregate and concrete. It's basically the weight of the concrete. It's basically the weight after you have soaked the brick in water for 24 hours, and then you wait for the surface to dry. This is surface dry saturated state. Okay? And then you minus the dry weight. So this is the weight of the brick when it's oven dry. There's no water in it. So that numerator there is basically the water, the mass of the water inside the pores. And then you divide it by the oven dry weight. And you multiply it by 100, and that gives you the absorption capacity. You've seen that formula before. Now, generally the standard is from ASTM that you actually soak it for 24 hours for clay oven bricks. But anyway, with most bricks, they will have an absorption capacity of about 5 to 10%. So remember, on one side of the coin, absorption capacity and porosity is a bad thing. Basically, water can get into the brick and break it down, and so the brick will slowly, through the years, disintegrate. So you're seeing that happen with a lot of the bricks in the old bazaar area. Have you noticed how the bricks are not actually a nice smooth cuboid? They're basically breaking down into smaller and rounder shapes. That's because their absorption capacity was probably a bit high. It might have been as high as 15%, I think, for them. But yeah, so absorption capacity is a bad thing if it's too high. However, you can't have it too low. Why is that a problem? if you have no absorption capacity, basically water in the mortar that will not react and bond with the brick, and so it won't stick. You can see that man, he's placing bricks there, and he's putting a mortar between the bricks. He wants those bricks to be able to stick together. If there was no porosity, they would not stick. It would just be like having two smooth glass blocks. You can't stick them together with concrete. Concrete needs to have some porosity in order for it to stick with two objects together. And so the standard that is used in America, that clay oven bricks, they need to have a porosity of greater than 3%. Lower than 3%, and the mortar just won't stick to them. But if it's too high, then they're not going to be durable. So normally it will be around 5 to 10%. That's normally what a clay oven brick will be. Now, why are concrete blocks so bad? Well, first off, it's very low insulation. They're made from very low quality concrete. You probably notice that when you look at it. It's not smooth, the concrete. It's all very rough with these concrete blocks. And that can give it really bad insulation. It also gives it very medium strength. I think the standard is they need to be 20 megapascals in strength, but I've seen research to say that in Kurdistan they can be as low as 5 megapascals in compressive strength, which is quite concerning, actually. But the good advantage of building it out of a low quality concrete is it's very cheap. I've heard a joke about from an Arab friend from Syria. He was a civil engineer in Syria, and they tend to use a lot more clay oven bricks there. But he says everyone's building out of concrete blocks here in Erbil because everyone's bakhil, meaning they're stingy. They don't want to spend money on good quality. So that's probably the main driving force for why we use concrete blocks. But I've got a question for you. Why can't we use high quality concrete for concrete blocks? Why can't we do that? Well, if we used high quality concrete, that would have a very low absorption capacity. And if it had, and I'm saying it would be lower than maybe 0.05%, very low. That will mean that the concrete blocks would not be able to stick to one another with the mortar. They would just be sitting on top of one another, and any person could come and knock over the wall. The mortar would not hold the blocks together in a masonry wall. So it needs to be a lower quality concrete to get the absorption capacity high enough that the mortar will actually stick to the block. So that's why it has to be cheap concrete for a concrete block and low quality. But of course that lowers the insulation and it also lowers the strength. Now, one of the reasons it has low insulation and low strength with this low quality concrete is because it has a very high void ratio. And you can see that it's all pocketed and pox-faced. It's not a smooth face to a concrete block. If you ran your hand up and down it for a while, it would feel like sandpaper. So it's got all of these little air cavities inside the concrete. I've got a question for you. Why don't these air pockets provide good insulation? We've already talked about that, haven't we? How air has very good insulating properties. It's only about 0.03 watts per meter Kelvin. Why doesn't it provide good insulation? Similar like the air pocket that is between two panels of glass in double glazed windows. Well, the reason is because this air is exposed to the atmosphere. The void ratio is so high that the void ratio are not individual air bubbles inside the concrete, but rather they are veins or channels that run through the concrete. So basically, the temperature that is outside will be the temperature that is inside, or potentially even worse. That's what causes the concrete blocks to be very poor insulators. If it was closed cell and the air particles were just bubbles inside the concrete, that would actually contribute to the insulation, but instead they're channels that run through the concrete, similar to Swiss cheese. Now this is another kind of masonry block that you've probably seen. So this is a type of masonry block. It's similar to the concrete block, isn't it? But you've probably seen them around. They're sort of this red colour, aren't they? Well, what's that made out of? Well, this is called a cinder block, and it's made in the same way as a concrete block. It's basically concrete, but unlike a normal concrete, which is a mixture of aggregate, cement and water, these cinder blocks don't have aggregate in them. Instead, they use lightweight and very low density cinder. What's cinder? It's basically ash. That's what it is. And ash, it's similar, if you like, to charcoal. It's got very low density. Now, that basically means that a cinder block will weigh a lot less than a concrete block. It will be a lot lighter. It has lower density. Now the issue with cinder is that it can actually react with any sort of level, or it's very reactive. If there's any kind of acidity in the atmosphere or moisture in the air, and water can act as an acid in the right conditions, it will basically evaporate, and so it will break down. And so with a cinder block, after they have made it, they need to spray it with this red coating. It's sort of a sulfur coating, and this basically acts like a paint that protects it from the acid that is sometimes present in rain. And so that gives it more durability. Now, it's less dense than concrete, so that makes it lighter. You also have to realize that concrete, it gets its strength from the aggregate. So aggregate is stronger than the cement in concrete. So however strong the cement is, that's how strong the concrete will be. However, with a cinder block, the cinders are actually weaker than the cement. So the cinders are basically just fillers. And so the strength of the cinder determines the strength of the block. And so they're actually very weak compared to concrete blocks. A concrete block will maybe have a strength of 5 to 20 megapascals. A cinder block, it might be maximum 5 megapascals. So that's a big thing you need to remember. We cannot use cinder blocks as a structural element for basically holding up a load. It can be used for walls that are not bearing a load, but it can't be used for structural walls. But the great advantage with cinder blocks is the low weight, and that's why we often use them in high rises. So that's a picture of a cinder block close up. So you can see first off there's sort of this red coating applied to it. That's basically a paint which protects it from the elements. But you can see all of those small little particles. They're actually basically clumps of ash, if you like, or clumps of cinder or charcoal. And so because of that, it's got very low density. So where we use them is high rises. Now look at this high rise. You can see here that we've got the superstructure of the high rise already, don't we? So with this high rise, we've got all of the strength is being provided for in the reinforced concrete columns. So we now need to fill in walls where you've got all of those gaps with masonry blocks, but they do not need to actually support the load of the building. The building is being held up with the concrete columns. However, we don't want to add too much weight to the building, because the heavier the building is, the higher the load there will be on those columns at the bottom. So using cinder blocks instead of instead of concrete blocks is a way of reducing the entire mass of the building. So this building is on Goulan Street, and if you go there now, you'll see they're actually building the walls using these red cinder masonry blocks, not concrete. So remember structural masonry versus non-structural masonry. So you can see this picture on the left. What are the columns and the walls made out of? Well, they're made out of masonry blocks, clay oven bricks in this case. And you can see that they are actually supporting the load. Those masonry walls are holding up the floor above it to build this two-story house. So in this case, the masonry blocks need to have some strength to them. However, on the right-hand side, this is a much bigger building, and you can see that actually it's being held up by a reinforced concrete superstructure with all of these columns and beams and joists and trusses. And so the walls that they're building there, they are not actually supporting any load. All they're doing is basically filling in the gap so that someone can live inside the building rather than on the building. And so in this case, it doesn't matter if the masonry block is low strength. What matters is that it's actually low weight, so you're not actually adding a lot of weight to the building and having to have bigger reinforced concrete columns. So normally structural masonry, we would use that for smaller buildings, usually no more than 2 stories, and we can usually find masonry blocks with enough strength in them. But for really big high rises, you're not going to get enough strength from masonry blocks, so you need to have reinforced concrete columns, and then you would have non-structural masonry to fill the walls. So that's an example of structural masonry versus non-structural masonry. Typically, structural masonry, we would use something like clay oven bricks or concrete blocks, and non-structural we might be, depending on how big the building is, if it's big, we might be tempted to use something like a cinder block. So this is a picture that I found in Slimani actually, and you can see there that they're actually filling in all the walls there with I think in this case it's actually oven clay bricks, They have a few more oven clay brick houses in Slimani. I think there's better availability of clay oven bricks in Slimani, and yeah, they're building it in a non-structural masonry way. That building is being held up by the reinforced concrete columns instead. So let's talk about reinforcement inside structural masonry. So as I said before, most bricks, most masonry blocks, they have very good compressive strength, but they have very low tensile and shear strength. Well, with a building, mostly it's going to be under, if it's a wall, it's mostly going to be under compressive loads. Basically, it's being squeezed. However, what happens if there's an earthquake and the building is being shaken left to right? Suddenly, all of the walls are going to be facing tensile and shear stresses. And if you don't have any tensile or shear strength, the building falls down. So how can you improve a building so it can withhold an earthquake if it's made out of masonry blocks? Well, the way you can do that is by combining masonry blocks with a material that does have a very good tensile or shear strength. Basically steel, reinforced steel. So remember how I said some blocks have cavities inside them? There's two advantages to that. One is that it actually reduces the overall, it means you can increase the surface area of the block without increasing the mass of the block. So you can basically build a wall of a given size with less masonry blocks. But the other big advantage is you now have these channels inside where you can put reinforced steel bars. And these bars have very good tensile and shear strength. So you set them in with concrete, and now if that building is in an earthquake, it's going to shake, but the steel bars are going to take the tensile and shear loads. So the masonry wall takes the compressive load and the bars take the shear and tensile loads. So this is very common. So you can see here, this is a picture I took in Abu Dhabi. I took this picture. This was a site I visited, and you can see there that they're building the walls there out of masonry, but you can also see that inside the masonry blocks they're setting reinforced concrete bars, and they're setting them in concrete inside the masonry wall. And so that's going to give it good structural integrity in shear stress as well as compressive stress. So that's what it looks like. You've got these bars going down into the foundation usually, and then you set them in concrete inside that so that they're all stiff. So finally, as I said, I think concrete blocks and cinder blocks are absolute rubbish in Kurdistan. They are very poor insulation. Your houses are way too hot in summer, way too cool in winter. If any of you want to think about developing a new masonry block using a different material, something like clay oven bricks or something similar to that, maybe this is an idea for a fourth-year research project. I've got a couple of students working on an interesting idea at the moment. But yeah, this is just a good research idea for you if anyone's interested, and if anyone's enjoying building materials and this is something you'd like to sort of specialize and research in fourth year, let me know. So finally, masonry materials. This is covered in the Somayaji book, pages 223 to 239, if you can get your hands on it. Otherwise, I hope to see you next week, where we will be beginning wood products and wood materials. And if you have any questions related to Assignment 5, which covers masonry, it's due on June the 14th, please let me know. Give me a phone call or email me. Make sure you get your assignment in on time, guys. Okay, guys, thank you and God bless. Bye.